So Carsten is from Munich and is doing his PhD with Claudia Krippelberg in the TUM and is going to talk about contagion in financial systems, a Bayesian network approach.
So first of all, let me thank the organizers for giving me the opportunity to speak at this conference here. It's my great pleasure to present this work here for this audience. So today I will speak about contagion in financial systems, and this is a joint paper with Claudia Krippelberg, also at TUM, and the preprint of the paper is already available on SSRN. So because not everybody in this audience may be familiar with what is systemic risk in the financial context, let me give you a short definition. So in this talk, systemic risk refers to the risk of a cascading failure in the financial sector caused by interlinkages within the financial system and resulting in a severe economic downturn. So the important point is really this cascading nature of systemic risk. Yeah? So it's really important to keep this domino effect picture in mind. So you have one bank with problems, and then other banks are linked to this bank, so problems are transmitted from one bank to the other, one in a chain, so to say. Okay. And of course, this is caused by interlinkages. So you see here an example of a banking network from Brazil with a lot of interlinkages between banks. Now, there's a lot of literature on systemic risk and also a lot of models already. So you may ask me, why do I want to come up with yet another model? All right. So the reason is, my goal is to present a model which has several, in our opinion, very important features for a systemic risk model. And up to now, to our best knowledge, the models in the literature only address some of these points separately, but there's no model yet which combines these points together. And actually, we present a quite simple model, in fact, which shares all these features. So I will present a model which incorporates stochastic dynamics, and it's not only based on deterministic network analysis, but you really have the stochastic component in it, where it's possible to identify channels of financial contagion. So if you have a bank which has problems, you want to know where these problems go. You want to know in which direction the contagion spreads. You also want to explicitly compute default probabilities, so not just qualitative results like saying, okay, if the network structure is like this, then the probability is higher or lower, but you really want to have a number in the end, okay? And you also want to quantify the systemic importance of institutions, saying which banks are more or less important for the system. And it should also be applicable to all network structures. So not only to some stylized networks which are homogeneous or coming from some random graph models, but really to any possible network. And so let me give you more details about the model. So I will consider N banks, capital N banks or financial institutions, and they will have a balance sheet of this form. So you have on the left-hand side assets. So you have operating assets which the firm uses to run its daily business, all right? And this will be a stochastic evolution. So this is at time t equals 0, and then it evolves in time. The firm also has some cash, and this is the part where the interlinkages between the firms comes into play. The banks have mutual loans or liabilities or bonds. It's all equivalent in this setting. So Lij represents the amount that bank I has lent to bank J at time t equals 0. And so you have the sum here on your asset side. And of course, on the liability side, you have some fixed liability to some external bank accounts, say the central bank, if you want. And also, of course, now in opposite direction, Lji from the other banks in the system, and some equity, which is the difference between assets and the liabilities. So the important point here is that we assume that there's no other form of mutual exposures between the banks in the system apart from loans or bonds. Okay, that's the assumption we make. Now, from time 0, we consider a one-period model to some time capital T. So T could be 1 for simplicity, or if you want. And what happens is that you have that the operating assets evolve, so it can get higher or lower depending on whether the bank performs well or not. Accordingly, the equity also changes, but I will assume that cash and liabilities don't change because I assume that there are no interest rates. So all interest rates are 0. You can put interest rates if you want, and it doesn't change the analysis at all. Okay. The important point is also what happens to the loans. Well, the rule is this: we say that Bank I gets back its loans from Bank J only if Bank J is solvent at time t. So if Bank J survives the game until time t. Yeah, if Bank J defaults, Bank I gets nothing at all. Yeah, so that's the rule. Now, first of all, about the stochastic dynamics of the processes xi. So I will assume a geometric Brownian motion for them, or a log normal distribution. In fact, this doesn't matter. So you can actually choose any other type of distribution you want. Yeah? So it's just for simplicity and for concreteness. Now, the solvency equation. So what do I mean by whether a bank survives or not? So a bank is called solvent at time capital T if it has a non-negative equity. This is quite intuitive. And in turn, the equity is the sum of the assets at time t minus liabilities. And what you see here is that these equations are coupled. So S depends on the equity, and the equity in turn depends on the set S. So you may ask yourself, well, can you solve these solvency equations? Is there a unique solution? And what can be said about the distribution of the solution? And I will in particular consider this distribution of the variables d1 to dn. So these are default random variables indicating whether bank I defaults or survives. Okay. And the first, let me first mention this. So the whole analysis in this talk is based on a graphical representation of the liabilities between the banks. So I will draw a graph on n edges, on n nodes, where each node represents one financial institution, and I will draw an edge from, in this example, from 1 to 4. If bank 1 has to repay 20 pounds to bank 4 at time t. Yeah, so an arrow means has to repay. Okay. Okay, and now the first theorem we have is this. So you have with probability 1 a unique solution of the solvency equations if and only if the liability graph has no directed cycles. So if it's a cyclic graph. Otherwise, you have at least, with a strictly positive probability, at least 2 solutions. And in the case where you have no directed cycles, you can prove actually that these variables, d1 to dn, indicating whether the banks default or not, form a Bayesian network over the liability graph. And this is quite, of course you have to prove it, but the intuition behind it is very simple. So consider this graph here with no directed cycles. So what you do is you first determine what happens to 1 and 2 because they don't depend on the other ones, so you can solve for them. Then if you have determined whether they default or not, you determine whether 4 and 3 default or not, and then whether 5 defaults or not. Yeah, so you can move through the graph and you have a direction because you have no cycles. Of course, if you have cycles, you cannot do this because after some point you have to go back. Yeah, and it's not clear how you what it means. And so this is the main part of this talk. So how do we deal with directed cycles, which are of course present in financial networks? So let me give you first an example of what the problem is. It's already a problem with 2 banks, and you see that there will be 2 solutions in this case. So let's consider 2 banks, each of them having 5 pounds at the end of the period, but they owe each other 8 pounds. Now there are 2 possibilities. Either you say, okay, well, they both default because neither of them is able to repay 8 pounds to the other one. No, they only have 5. Or you say, well, they owe each other 8 pounds, so just forget these 8 pounds. Just cancel them. And both of them survive with 5 pounds. Yeah, so it really depends on whether you allow for netting mutual claims within a directed cycle. And this is where the non-uniqueness comes from. Okay. And you can imagine this happens for all possible cycles. You have to make this decision. And the goal of the subsequent analysis is now to characterize the solution with the highest number of defaulting firms and the solution with the smallest number of defaulting firms. Yeah? And I will call these the solutions according to the strict default rule or the mild default rule. Strict if you have a high number of defaulting firms, and mild if you allow for netting and therefore have the smallest number of defaulting firms. And I will concentrate on the mild rule now, because for the strict rule it's analogous. Okay. Actually, what we can show is that the default random variables, according to the mild default rule, can actually be determined via a simple algorithm. So what you do is this. So first of all, you assume that all firms repay their debts. And you ask yourself, well, is there a bank in the system which is still not able to repay its own debts to the other ones? So is there still a bank with negative equity? If so, then of course this bank has to default, and you put it into the set D1. Next step, you ask yourself, okay, now I assume that all firms repay the debts except for those where we already know that they default, namely in D1. And now the question is there a new firm now that has problems and is unable to meet its obligations? If so, put them into D2. And you do this several times, and after n steps, you're finished, and this gives you the set of defaulting firms and the complement the solvent firms. So you see what happens here is really that default spreads through the system. You have at the beginning a small set D1 of firms that are defaulting, and then there will be this contagion, and this will spread to a larger set of firms. Okay. Now, so still we would like to know something about the distribution of the default variables under the mild default rule. Of course, we cannot get a Bayesian network structure in this case because we have directed cycles, and Bayesian networks are a priori defined on DAGs, on acyclic graphs. Yeah, so what is the idea? The idea is now, okay, to say, okay, we incorporate this cascade structure of the mild default rule directly into the graphical representation. Yeah, so we expand the original liability graph, which has directed cycles, into a bigger graph without cycles, and try to recover a Bayesian network structure on this augmented graph. Yeah, and I'm sorry that I cannot explain this augmentation procedure in detail because due to time limitations. So I just show you this small example here. So what you have is, instead of a directed cycle 1, 2, 3, 4, what you have now are copies of 1, 2, 3, 4, and you see this flow structure from left to right. Yeah, and that's what we do here. And this corresponds to this mild default rule algorithm. Accordingly, you define variables din corresponding to whether the firm I has defaulted up to the nth step of the mild default algorithm. And then you can prove that actually under this mild rule, these variables form a Bayesian network on this augmented graph I've just shown you. And the conditional probabilities can be explicitly calculated. If you want, you can look up the formulas in the paper. I didn't write them down here. And of course, the variables we are interested in, d1 to dn, are now the marginal distribution of one marginal distribution of these this extended random vector, right? So you can get a Bayesian network structure back on this extended vector. So you may ask, what is all this Bayesian network structure thing good for? And actually, there's a lot of theory, of course, on Bayesian networks, and this theory allows us to meet these goals I've listed at the beginning. So for instance, using the notion of deseparation, this allows us to detect contagion channels to say where are the conditional dependencies within the graph. You can measure systemic importance by using classical probability distances, and also compute explicit default probabilities using classical algorithms. Okay. Because I'm running out of time, I just show you a little example here. So you have here 100 banks 5 of them are very important, so they're in the center and they form a complete graph. So all lending relationships are present, and you have attached to each of these core banks 19 smaller banks, periphery banks. Yeah, and you have some parameters here. And what this graph shows is the distribution of the number of defaulting institutions in percentage on a log scale. So you can have 0 defaults up to 100. And the important thing, what you see here, is really this systemic risk factor, which says that this distribution is not monotonic. It has several local maxima. Yeah, and each local maximum corresponds to a defaulting core bank. So it's if the core bank defaults, it's not only this bank defaulting, it really will typically drag a lot of periphery banks into default as well. So you see these local maxima corresponding to no 1, 2, 3, 4, and 5 core banks defaulting. Okay? So let me summarize. So I presented a systemic risk model which satisfies some, as we believe, important properties. So this is again what I've listed at the beginning. And from the mathematical point of view, I think this is also interesting because we presented a method how to transform directed cyclic models into acyclic models, into Bayesian networks. And we give an interpretation of directed cycles as cascade paths with a starting point which is indeterminate. Yeah? So it's unknown where it starts, so therefore you have this cycle. And so at this point I should really stop and thank you for your attention.
Okay, any questions? Just one question, or maybe Jazine? Yeah.
It's very nice work. It's quite intriguing.
Yeah.
So you achieve a lot of simplicity by having this graph, so the network structure, which is just connected or not connected. So two firms are connected even if they owe each other a penny, right?
Yes.
So if you put weights directly on the connections, which the weights referring to how much they owe each other, would that make things much more complicated?
I mean, actually, there are weights on the edges. So this is the Lij's. Mm-hmm. And actually, of course, the default probabilities, the conditional probabilities depend on these weights. Mm-hmm. And if it would, of course, be simpler if you say if it's just 1 penny, then we forget it, because this will not make a big difference. So this is something you have to choose in practice. So what do you mean by a significant liability, and which liabilities do you neglect? Yeah.
It's very interesting. I would add a last point from a policy perspective. Since you can trace the propagation process, that this is very important information for the central bank when to intervene. So you can simulate the intervention of the central bank in order to stop the propagation of the process. Yeah. So you can exactly know where the central bank should intervene.
Yeah. So you can say that with a high probability it should be this node. So it's all probabilistic statements. So you cannot be sure, of course, but you can say this should be the one we attack first or we help first. Yeah, it's true. Thank you.
Final question? Okay, so let's thank Carsten again. So now it's time for the